Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on Introduction to the Power Electronics. Now here one of the most advanced and research-oriented subject, that is power electronics. So here we have two words. First one is the power and second one is the electronics. So what is meant by power? Power means high amplitude voltage and current. It handles high power in the range of, in the order of in the kilowatts to the kilowatts or megawatts. Mainly it concerned with high efficiency, high efficiency. If you see the power engineering definition, power engineering mainly concerned with generation, transmission, distribution and utilization of power at higher frequency. The efficiency must be high with low losses. And next, what about electronics? Electronics means here low power in the order of milliwatts. So here we will not consider efficiency. Without much consideration of efficiency, here power is transmitted, data or signal is transmitted from the source to the load with minimum possible distortion. Here if you see the definition of electronics engineering, it deals with distortionless production, transmission and reception of data and signal of very low power in the range of, in the order of milliwatts without much consideration of efficiency. Now power engineering and electronics engineering. Now see the power electronics definition. So the definition of power electronics is a subject, so that concerns the application of power electronics principles in the power engineering to improve the efficiency of the system. Here the losses must be minimum when power is transmitted to the generating station to the consumers. So now here in another way we can define this power electronics. It is a technology, it is a subject, is associated with efficient conversion and control of electrical power by power semiconductor device. So power power can be electrical power. Here the power may be, so using power converters or power controllers, so we can control one form of electrical energy to the another form of electrical energy to the load by using semiconductor devices like SCRs, GTOs, triacs. So now here block diagram of power electronics controller. So now here block diagram of controller, it looks like this. Here first one is a power source and second one is a load, and here in between this power source and load there may be a power controller or power converter. And there may be a sensing and feedback circuit, and here control unit and reference setting and commands. Here power is transmitted to the load consumers. Here in between these two power controller, here the power source may be a generator, battery, AC supply. Here this power is transmitted to the load. Here there may be a power controller. Power controller means here this controller converts one form of electrical energy to the another form of electrical energy. Here another one is a sensing and feedback circuits. Sensing and feedback circuits means here these sensing and feedback circuits monitors the load. So now here this feedback circuit is that commands is given to the control unit. So this control unit consists of drive circuits. So this control consists of drive circuits of power controller or power converter. So now here when there is a error, so there may be an error. So here there may be an error, the difference between reference setting commands and sensing and feedback circuits. Then this control unit adjusts this driving circuits, and this is given to the power controller. So this is regarding the block diagram of power controller. So now here, so why we need to study this power electronics subject. So now here, why we need to, now let us take the scenario of energy scenario. Here electrical energy is generated from the 87% of electrical energy from the fossil fuel, and say out of which 70% from the coal thermal we will generate the electrical energy, and next 6% of electrical energy generated from the nuclear energy, and rest of the electrical energy generated from the renewable energy like solar, wind and hydropower. And next here, we know that after 100 years, after 50 years, this non-renewable energy sources may not be available after 50 years. So nuclear will not be available, and next fossil fuel thermal coal will not be available after 100. So after 100, what will happen after 200 years? So there is no question. So maybe, so now here, so we can extend this period, so by using power electronics devices. So now if you so we can extend this period. So how we will extend? So see this diagram. So fuel turbine generation transmission load. So this scenario, if you give 100 kilowatt power to the fuel energy is given to the turbine, so finally you will get here 16 kilowatt 16.5 kilowatt power only here. So here if you give 100% of fuel energy, here you will get 16.5% of energy you will get. So remaining 83.5 is a loss. So now here there may be 6:1. Here input is 6 and output is 1. So now here, so there is a one question. So why to spend so much of time at front end only? Here if you, for every 1 kilowatt at load side energy saving, so the results in 6 kilowatt power at front end. So now here in this way we can save the energy in this way by using power electronics devices. Here improve the power conversion efficiency, and we can improve the percentage of renewable energy sources. And next here, second thing, here there may be a from this example also we can so if suppose here we are giving 200 volts, here 198 volts back EMF in the DC motor. So here EB equals to Zn5 by 60 into P by A. So this is the formula. EB is directly proportional to the N. So now E1 by E2 equals to N1 by N2. If suppose this motor speed is 1000 RPM. So now if you want to reduce this speed of the DC motor is 500 RPM. So now how we will reduce this one? So now here this is back EMF is 198 divided by E2 equals to 1000 by 500 RPM. So that equals to E2 equals to 99 volts. So if it is 99, if it is E2 should be 99 volts, means this is 200 volts. So the here if you connect to one resistor across this, then external resistance across in between this source, this voltage source and here, so that that resistance is so 101 volt. So that voltage drop across this resistance is 101 volts. Then that speed must then we can reduce the speed. But here that 101 volts is a voltage drop, resistive drop. So because of this there must be huge amount of power loss. So this is power loss. So here by attaching one power electronics device, one switch, so then we can reduce the power loss. Here by using power electronics devices we can reduce the power loss. In this way we can increase the power, we can increase the efficiency of the system, efficiency of this one. And after that another one we in the second example, so in the transformer maximum power, maximum efficiency occurs at iron losses equals to copper losses. Copper losses equals to I square R. So by varying resistance, by varying load, so we can increase it. But here copper losses are fixed. This is depending on V by F ratio. By variable voltage and variable uh, uh, frequency, we can maintain the constant V by ratio by using power electronics devices. So here variable voltage, variable frequency and variable load, we can maintain the constant iron losses, and iron losses equals to copper losses, and then we can maintain the PI equals to P copper, and then we will get the maximum efficiency. So in this way, by using power electronics devices, semiconductor devices, we can increase the efficiency of the power. And next here, what are the advantages? Here, fast dynamic response due to the static devices, and second one is the high efficiency conversion from AC to DC or DC to AC, AC to AC and DC to DC due to low losses in the electronics devices. And next, compact size and lightweight of the controller. And next here, increased operating life and reduced maintenance since there are no moving parts. And next here, its operation is very flexible. And next here, electromagnetic interference and noise will be reduced by using power electronics devices. And next here, what are the disadvantages? Here there may be a harmonics will generate in the power electronics controllers. So these harmonics will affect the performance of other loads in the network, in the systems. And next here, power factor of power electronics controller are very low. So very low means here, so power factor is cos phi is very low means here, so we need to power factor correction. Power factor correction is required. So here this is power factor. So this is active power, this is reactive power, this is apparent power, this is power factor, cosine angle between voltage and current. So now here this is reduced means in order to reduce the reactive power, so we need to correct the power factor. And next, the last disadvantage of this this power electronics controller is cost. Cost is very high of power electronics converters. And next here, applications. What are the applications of here? So applications of power electronics, in the power control, we will use these power electronics devices in the resistance welding, induction heating, electrolysis and process industry, etc. we will use. And next here, in the power conversion of HVDC, high voltage DC transmission and high voltage AC transmission, HVAC transmission systems we will use. And next, speed control of DC motors, so which are used in the traction drives, textile mills and rolling mills, cranes, lifts, compressors and pumps. So these are the applications. So in which we will, in these motors, for speed control we will use power converters. And next, in the UPS, standby supplies, emergency power supplies for critical loads. What are the critical loads? Computers and medical equipment. We will use this UPS, uninterrupted power supply, standby power supply, emergency power supplies. And next here, high voltage power supplies for electrostatic precipitators and X-ray generators. And next here, power supplies for communication system, telephone exchanges, satellite systems. We will use these power electronics devices. So these are in the power control, power conversion, speed control of motors, in the UPS, in the power supplies, high voltage supplies, in the power supplies, we will use these power electronics controllers. And next here, in the solid state power compensators, static contactors and transformer tap changers. And next here, what are the types of these power converters? Types of AC to DC converters, that means controlled rectifiers, and DC to AC converters, that is inverters. And next here, DC to DC converters, that means choppers. And next here, AC to AC converters means cyclo converters, and next AC to AC converters, that means regulators, AC regulators. So now here if you see this one here, first one, AC to AC converters means controlled rectifiers. Rectifier converts. So here AC supply to the variable DC here. So this is one converter. It will convert AC to DC. It should be variable DC. So here what are the applications of this converter? This is controlled rectifier is DC drives we will use in the uninterrupted power supplies, UPS, HVDC system, and next AC to DC. So AC to DC means here, so this is, so DC to AC, this is inverter, DC to AC. This here fixed DC we are giving input to this one. This is inverter, and variable frequency and variable voltage we will get the output side. This is regarding inverter. So here we will use for speed control of induction motor, we will use inverter. Standby power system, standby power supplies, and emergency power supplies for critical loads. Critical loads means computers and medical equipment. Here the pump drives we will use in the induction heating, and in the UPS, uninterrupted power supplies. Here from the batteries, AC supply will generate using these inverters, and next AC drives. So it will convert from fixed DC voltage to the variable AC voltage and variable frequency. And next, what about the choppers? So here DC to DC converter, here the output is DC to DC. So now here fixed DC voltage to the variable DC voltage, and next here there are different types of chopper, step up chopper, step down chopper, buck converter, boost converter. These are SMPS. Here these are used in the SMPS, DC motor drives, traction drives, speed control of DC motor. Now here inverters are used in speed control of DC motors, and choppers are used for speed control of DC drives. And AC to AC converters, that means cyclo converters. These are also AC converters, AC to AC converters, but these are AC converters. What is the difference between? So same input AC here, output is also AC, same here. Output is also same AC here, but here only the difference. This one is also variable AC, and this one is also variable AC, but here same type of frequency. Here this one, here this is same type of frequency, it is variable frequency. Here this cyclo converters are two types: step up cyclo converters, step down cyclo converters. So these are used in AC traction drives, and same way here this AC voltage regulators are used in the speed control of large fans, pumps, heat control. So now rectifiers, inverters, choppers, cyclo converters, AC voltage regulators are the 5 types of power converters. And next here power semiconductor devices. So these are 3 types. First one is diodes, and second one is a thyristor, and third one is a transistor. So now here if you see this one, so diodes are 3 categories. General power diodes are 3 categories: general purpose diode, and fast recovery diode, and Schottky diode. Diode symbol is, it looks like this, anode and cathode. So now here general purpose diode, the rating, voltage and current rating at 50 volts to the 5 kilovolts, and this one fast recovery diode, that means that means here 50 volts to the 3 kilovolts, and 1 amp to the 1 kilo amperes. And next Schottky diode means here 300 volts is the voltage rating, and 1 to 300 ampere is the current rating. And next, what about the transistors? Transistors means power BJT, power MOSFET, IGBT, and SIT. Here power BJT symbol. So this is NPN, and this one is a PNP transistor, power BJT. and this is collector, emitter, and this one is a base. And next, what about the power MOSFET? Power MOSFET symbol, it looks like this. This is N channel, drain, source, and gate. And next, here this power BJT voltage rating and current rating 1400 volts and 400 amperes, and power MOSFET 1000 volts and 50 amperes. And next, here IGBT symbol is here. This one is collector, emitter, and this is gate. So 1200 volts and 500 ampere. Next is SIT. So 1200 volt by 300 ampere. Next, here in the thyristor category, so SCR, silicon control rectifier, GTO, gate turn off thyristor, and RCT, reverse conducting thyristor, LA, SCR, so light activated SCR, MCT, mass controlled thyristor, triac. So here triode for AC, here SIT, static induction thyristor. Here these ratings are 7000 volts by 500 ampere for SCR. So SCR symbol is anode, cathode, and this one is gate. And what about the GTO? So GTO symbol is same like this. This is anode, this is cathode. So this rating is 500 volts to 300 amperes. So now here this GTO, this is here. Another one is entering and another one is leaving. And RCT means 2500. RCT means here there is a thyristor and across this one diode. That is this rating is 2500 by 400 amperes. And Lasker means here this one. This is anode, cathode, and gate. And next here MCT, mass controlled thyristor. So this one is here anode, cathode, and gate here. And next here this one is a MCT. So this voltage rating is 1200 volt by 40 amperes. And triac means here. So this one is MT1, MT2, and this is gate. So now here this voltage rating 1200 volts by 1000 amperes, and static induction thyristor is same like this here, anode, cathode, and gate. So now these are the power semiconductor devices. I hope all these concepts are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.